In this lecture, we're going to look at the different types of circuits that might show up. We're going to look at a series circuit first. You'll notice here that we have a battery connected to a switch with 3 light bulbs, and they're all connected in series. In other words, they are connected one right after another. If you turn one light bulb off, the rest of the light bulb will turn off as well. Series wiring means that the devices are connected in such a way that there is the same electric current through each device. There's only one loop for the current to travel in. You may see a circuit drawn like this as well. This is the symbol for the battery down here. The plus side is the longer side. The current travels from plus to negative, so the current travels through this ammeter, coming through, travels through the resistor 1, through resistor 2, through resistor 3, and back through this ammeter. The reason why it's not the flow of electrons that we look at is because Ben Franklin chose the wrong direction, so we look at the flow of positive charge. This V1 is the voltage drop across the first resistor, this V2 is the voltage drop across the second resistor, and V3 is the voltage drop across the third resistor. And you'll see here the rule is that VB, in other words the total voltage here, is just the voltage drop across the first resistor plus the voltage drop across the second resistor plus the voltage drop across the third resistor. This is the rule for total voltage. The rule for total resistance is that you just add up the resistors. R1 plus R2 plus R3 is the total resistance. And it says here the equivalent resistance is equal to all the resistors added up. Equivalent resistance is a term used when you want to replace a number of resistors by just one resistor. This many times makes problem solving easier. So you're going to want to pause the video right now and write down all these equations here. That the effective resistance in a series circuit is R1 plus R2 plus whatever resistors are in series. The total voltage of the battery or the power supply is just the voltage drop across the first resistor plus the voltage drop across the second resistor plus the voltage drop across any other resistors. And this equation here says that the current coming out of the battery equals the current going through the first resistor, which equals the current going through the second resistor. And it equals the current going through any other resistors as well. So here's an example of we have a 6 ohm resistor and a 3 ohm resistor are connected in series with a 12 volt battery. Assuming the battery provides no resistance to the circuit, draw the picture. And we also want to find the current through each resistor, find the potential drop of each resistor, the power dissipated in each resistor, and the total power delivered by the battery. So if you go back to that previous screen and write down all those givens and draw that picture, you'll be all set. So here's our drawing for this problem, and the first thing we want to solve for is to find the current in each resistor. Now, to find that current, we have the total current coming out here. It actually goes through each resistor. So if I solve for the total current, I'll be all set. And what I can do is use total resistance equals total voltage over total current, and this is just Ohm's law, and I have to make sure I do the totals though. I have to make sure that the subscripts are all the same. So the total resistance here is just the 6 ohms plus the 3 ohms gives us 9 ohms. So I'll plug that in here, my 9 ohms. And my total voltage is the 12 volts. And I want to solve for that total current. So I go ahead and solve for total current. It ends up giving me an answer of 12 divided by 9, which is about 1.3 amps. So there's our first answer. Now I want to solve for the potential difference across each resistor. So in the next part, I want to solve for V1, the potential difference across the first resistor. Well, if I just look at Ohm's law, that's just I1 times R1. And I know the current is the same in each resistor, so I know it's 1.3 amps, or 1 1/3 amps, and the resistance is 6 ohms. So I go ahead and just plug in that 6 ohms there, multiply that out, and I end up with a potential about 8 volts. Now I know automatically that the 3 ohms has to be 4 volts because the two have to add up together. So I know it's 4 volts here because that all adds up together. So V2 has to equal 4 volts. Or I could have done V2 equals I2 times R2 and come up with the answer as well. Now in order to solve for the power dissipated in each resistor, we have to use the power equation. In order to calculate that power dissipated, I can use power equals I times V. We could also use V squared over R or I squared times R. Any one of those power equations will work. The IV will work just as fine. The power dissipated in the first resistor is the current 1.33 amps, or 1.333 amps, 1/3 amps, times the voltage drop across that first resistor is 8 volts. I multiply that out, I end up with a power of about 10.7, and the units for power is watts. And I'll do the exact same thing for the power in the second resistor. Again, it's 1.33 amps going through that resistor times the 4 volts. Ends up giving me a power of 5.3 watts. And then they ask, well, what's the total power? Well, you would just add those together and get a total power of 16 watts. Or you could have done current times total voltage, either one. Now we want to take a look at the parallel circuit wiring. Here you see that there's a battery right here, there's a switch right here, and when that switch is closed, the current will flow along through the switch, and now it has a junction where it has two choices. It can go either straight through this light bulb or to the first light bulb, or it can go up to the second light bulb. So now you have two loops, more than one loop, and that's when you know you have parallel wiring. Parallel wiring means that the devices are connected in such a way that the same voltage is applied across each device. There's more than one loop for the current to travel in. So here's another example of a parallel circuit drawn. You have current coming out of the battery here, coming up, you'll see the current here, and it breaks up into these three other currents. So the current coming out of the battery is split at the junction, and the junction part of the parallel circuit, and you'll notice that this current, this total current here, has to equal I1 plus I2 plus I3. Every time you add a new resistor in parallel, the total resistance of the circuit goes down. Just like when you add a lane to a highway, you make it easier for cars to travel. Adding a resistor in parallel gives the current one more lane to travel in, the total resistance goes down. So here are equations that we use for parallel circuits. 1 over the effective resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. The total current coming out of the battery equals the current going through the first resistor plus the current going through the second resistor, and so on. And the total voltage at each resistor is exactly the same. So the total voltage from the battery equals the voltage at the first resistor, which equals the voltage at the second resistor, and so on. So here we have a problem where we have two resistors, 42 and 64 ohms, are connected in parallel. Current through the 64 ohm resistor is 3 amps. I want you to draw the picture now. So pause the video and draw that picture. And I want you to find the voltage drop across each resistor, the current through the first resistor, the voltage of the battery, and the current coming out of the battery. So write those down as things you want to solve for, and go ahead and we'll do that. And in this, I've drawn the picture, and in this problem, we don't know much about the current, except that the current is 3 amps going through the 64 ohm resistor. And if we want to find the voltage drop across each resistor, what we do is find the voltage drop across this first resistor. We're going to call this R1, and we'll call this R2. We'll find the voltage drop across that first resistor. So we use Ohm's law, V equals I times R, making sure I keep my subscripts consistent. And my current is 3 amps. The resistance is 64 ohms, so when we calculate that, we end up with a voltage across that first resistor of 192 volts. Now, since we're dealing with a parallel circuit, we know that the voltage drop across the other resistor is 192 volts also. We know that the voltage drop is the same across each resistor. So we know V1 is 192 volts and V2 is 192 volts. The current through the first resistor, actually I guess I'm calling that the second resistor. So we can find the current through the other resistor is, we call that V2. And so we'll just say I2 equals V2 over R2. It's 192 volts over 42 ohms. And so that ends up equaling a current of about 4.6 amps. So we know up here that we have 4.6 amps going through that resistor. So actually we know what the total current coming out of the battery is. I'm kind of skipping to the last one. The current coming out of the battery is just those two added together. That total current ends up equaling the I1 plus the I2. That total current ends up equaling 7.6 amps. So that's the total current coming out of the battery. And we also know that the voltage drop across the battery has to be 192 volts as well. We know that the voltage drop is the same. The voltage gain here is the same as the voltage drop up here, 192 volts, and the voltage drop up here, 192 volts.